Differential form. History. Differential forms are part of the field of differential geometry, influenced by linear algebra. Although the notion of a differential is quite old, the initial attempt at an algebraic organization of differential forms is usually credited to Élie Cartan with reference to his 1899 paper. Some aspects of the exterior algebra of differential forms appears in Hermann Grassmann's 1844 work, Die Lineal Ausdehnungslehre, ein neuer Zweig der Mathematik, the theory of linear extension, a new branch of mathematics. Concept. Differential forms provide an approach to multivariable calculus that is independent of coordinates. Integration and orientation. Multi-index notation. The exterior derivative. Differential calculus. Intrinsic definitions. Operations, as well as the addition and multiplication by scalar operations which arise from the vector space structure, there are several other standard operations defined on differential forms. The most important operations are the exterior product of two differential forms, the exterior derivative of a single differential form, the interior product of a differential form, and vector field, the Lie derivative of a differential form with respect to a vector field, and the covariant derivative of a differential form with respect to a vector field on a manifold. Exterior product. Riemannian manifold. Vector field structures. On a pseudo-Riemannian manifold, one forms can be identified with vector fields. Vector fields have additional distinct algebraic structures, which are listed here for context and to avoid confusion. Firstly, each cotangent space generates a Clifford algebra, where the product of a covector with itself is given by the value of a quadratic form, in this case, the natural one induced by the metric. This algebra is distinct from the exterior algebra of differential forms, which can be viewed as a Clifford algebra where the quadratic form vanishes, since the exterior product of any vector with itself is zero. Clifford algebras are thus non-anticommutative quantum deformations of the exterior algebra. They are studied in geometric algebra. Another alternative is to consider vector fields as derivations. The non-commutative algebra of differential operators they generate is the Weyl algebra and is a non-commutative quantum deformation of the symmetric algebra in the vector fields. Exterior differential complex. Pullback. Integration. A differential K-form can be integrated over an oriented K-dimensional manifold. When the K-form is defined on an n-dimensional manifold within K, then the K-form can be integrated over oriented K-dimensional submanifolds. If K equals 0, integration over oriented zero-dimensional submanifolds is just the summation of the integrand evaluated at points, with according to the orientation of those points. Other values of K equals 1, 2, 3 correspond to line integrals, surface integrals, volume integrals, and so on. There are several equivalent ways to formally define the integral of a differential form, all of which depend on reducing to the case of Euclidean space. Integration on Euclidean space. Integration over chains. Integration using partitions of unity. There is another approach, expounded in Diuda 1972, which does directly assign a meaning to integration over M, but this approach requires fixing an orientation of M. The integral of an n-form O on an n-dimensional manifold is defined by working in charts. Suppose first that O is supported on a single positively oriented chart. On this chart, it may be pulled back to an n-form on an open subset of Rn. Here, the form has a well-defined Riemann or Lebesgue integral as before. The change of variables formula and the assumption that the chart is positively oriented together ensure that the integral of O is independent of the chosen chart. In the general case, use a partition of unity to write O as a sum of n-forms, each of which is supported in a single positively oriented chart, and define the integral of O to be the sum of the integrals of each term in the partition of unity. It is also possible to integrate K-forms on oriented K-dimensional submanifolds using this more intrinsic approach. The form is pulled back to the submanifold where the integral is defined using charts as before. For example, given a path GT 0, 1, R2, integrating a 1 form on the path is simply pulling back the form to a form ft dt on 0, 1, and this integral is the integral of the function ft on the interval. Integration along fibers. Stokes's theorem. Relation with measures. Currents. The differential form analog of a distribution or generalized function is called a current. The space of K currents on M is the dual space to an appropriate space of differential K forms. Currents play the role of generalized domains of integration, similar to but even more flexible than chains. Applications in physics. Applications in geometric measure theory. Numerous minimality results for complex analytic manifolds are based on the Wirtinger inequality for two forms. A succinct proof may be found in Herbert Federer's classic text Geometric Measure Theory. The Wirtinger inequality is also a key ingredient in Gromov's inequality for complex projective space in systolic geometry.